action. My talk is about multi-interface and multi-layer Kelvin-Helmholtz instability and Rayleigh-Taylor instability. We consider this kind of multi-layer flows with density stratification and velocity shears like this. Then these interfaces become unstable and roll up like this. This is a typical multi-layer vortex sheets, which correspond to three-layer two-interface Kelvin-Helmholtz instability. This is a typical multi-interface flows when the system is unstable. But in the current study, we consider another one such that the interface do not roll up simultaneously like this. Now, this is the background of this study, or my motivation. My motivation is that, is it possible to suppress KHI, RTI, and RMI, Richtmyer-Meshkov instability, without external forces or surface tension? For this topic, one of the studies is the one by Michaelian. He insisted that it is possible to suppress the linear growth of RTI when the system is multi-layer and adequate initial condition and density ratios are selected. He called this phenomena freeze out or freezing out in his studies. He performed some linear analysis for the temporal evolution of bubble and spike amplitude and obtained some solution to some ordinary differential equations. But how about the multi-layer KHI, or how about in the nonlinear region? Unstable multi-interface or vortex sheets usually strongly interact with each other and roll up simultaneously, as I show you on the cover page. But Moore suggested that there is a case that two vortex sheets evolve independently under certain conditions, even though they are sufficiently close to each other. And what initial conditions can such interfaces be realized? How do they behave in the nonlinear region? What happens when those conditions are satisfied? Is it possible to suppress the growth of the interface? For this, it is possible to some extent. This is one of the answers to those questions. Now we consider in the current study the following physical conditions. One, the flow is incompressible and inviscid potential flow. Two, uniform velocity shear exists on interfaces at t is equal to 0. Three, initial conditions are linear progressive waves because we consider Kelvin-Helmholtz instability. This is the schematic figure in this study. So I briefly explained the Moore's condition and Moore's conjecture. Donald Moore considered this kind of multi-layer flows And he set these velocity shears where U2 is the velocity shear at the lower interface and U0 is the velocity shear at the upper interface. And he assumed that this condition, that is, the lower velocity shear is approximately equal to minus U0, the upper velocity shear, and he assumed that the amplitude A2 here, amplitude of the lower interface is approximately 0 at t is equal to 0. He assumed these conditions. We call this condition Moore's condition here. And he derived a critical time TC here by some heuristic way, where d is the distance between two interfaces and theta is a parameter within this range. He concluded that when t is less than tc, the motion of the upper interface is determined only by U0, and it is not affected by U2. That is, the upper interface behaves as if the lower interface does not exist, where Tc does not depend on the wave number k. In the linear theory, as U2, the lower velocity shear U2, tend to minus U0, which corresponds to theta tends to 1 here. Then Tc, the critical time Tc, tends to infinity, as you can see. When t is greater than Tc, the linear theory breaks down and it cannot tell anything about the evolution. Two interfaces move independently when Moore's condition is satisfied. We can expect this thing. Here we call this thing Moore's conjecture in this study. So simultaneous roll-ups we showed you on the cover page. Such simultaneous roll-ups do not occur when Moore's condition is satisfied. We can expect this kind of thing. So then the behavior of the two vortex seeds in the nonlinear regime is unknown because Moore's analysis is a linear analysis. So the gravity effect or the density stratification is not included in Moore's analysis. In the current study, considering this, we find initial conditions corresponding to Moore's conjecture and calculate the long-term behavior that is a nonlinear motion of two vortex seed systems, that is multi-layer Kelvin-Helmholtz instability or Rayleigh-Taylor instability using the vortex seed model. Now this is the result of linear analysis. These are linear analysis to find Moore's condition. These are initial conditions for numerical computations. Now we define Moore's condition as follows. U2 is equal to minus U0, and the amplitude of the lower interface is approximately 0 initially. For the amplitude, here the amplitude A1 is the amplitude of the upper interface. The amplitude of upper interface is far greater than the lower amplitude. This is the assumption. Then the governing equations for the linear analysis are as follows. We assume the potential flow, then the bulk, in the bulk, Laplace equation hold. At the interface, Bernoulli equation holds like this. And also, kinematic boundary conditions, that is, normal velocity continuous conditions, must hold at each interface. Then linear dispersion relations are obtained from the analysis. The dispersion relation is described by the fourth order algebraic equation for the frequency omega. We solve this equation by the Newton's method because the fourth order for omega. Then at the same time, we can obtain the amplitude of the lower interface as follows by this dispersion relation. This is the result of the dispersion relation. Now we consider 4 cases in this study. Case 1 is this case, that is, all the densities of fluids are the same. Rho 0 is equal to rho 1, and rho 1 is equal to rho 2. This is the Muir's case. And for case 1, we assume that the Muir's condition is satisfied. Then the left figure shows the imaginary part of the frequency omega, and right figure shows the amplitude of A2, the lower interface. Case 2 is also the same density situation, that is, all densities are the same, that is, fluid is uniform. And but in this case, Muir's condition is not satisfied. These are case 1 and case 2. The rest of 2 cases are as follows. Case 3 is this case. And in this case, stable density stratification exists in this case. And also, Muir's condition is satisfied for this case. And the last one, case 4. In this case, unstable density stratification in this for this case, and also Muir's condition is satisfied in this case. We consider these 4 cases and compare those in the nonlinear region. Any mode eventually becomes unstable because we consider uniform velocity shear initially. So any mode eventually becomes unstable, of course. But mode with the largest imaginary part of omega, with the largest omega I, the imaginary part of omega, increases fastest. This is the fastest mode. In all cases, the amplitude A2 is approximately 0 at around this wave number. This wave number is approximately 1. So we set k is equal to 1 in numerical calculations for all cases. This is the nonlinear analysis. We adopt the vortex sheet model. Vortex sheet model is a mathematical model to describe the nonlinear motion of anyway, this is a vortex sheet model, and we skip the details. We skip the details, and the result is as follows. Case 1, the left figure shows the interfacial shape and vortex sheet strength. The color bar denotes the vortex sheet strength. The upper figure shows quite an early time, and the last one is the final stage of the computation. And the right figure shows the velocity field in case 1. Case 1 satisfies the Moore condition. As you can see, the upper vortex sheet rolls up independently of the lower vortex sheet, and lower sheet does not roll up like the upper sheet up to the final stage of computations. That is, Moore's conjecture is maybe correct even in the nonlinear regime. This is case 1, uniform density case. And this is case 2. This is the interfacial shape and vortex sheet strength, and this is the velocity field. For this case, Moore's condition is not satisfied. As you can see, when Moore's condition is not satisfied, the lower sheet begins to roll up like this in the nonlinear regime. And the strength of the lower sheet finally becomes stronger than that of the upper sheet. Both vortex sheets largely roll up in the nonlinear stage. This is case 3. The stable stratification in this case. In this case, Moore's condition is satisfied. As you can see, the independence of the two interfaces is more noticeable compared to case 1, previous one, without the density stratification. The lower sheet hardly deforms up to the final stage of computations, and the region between the two sheets maintains a state of stagnant flow. That is, there is no flow between two interfaces, like this. In the case that the upper fluid is lighter than the lower one, the same result is obtained even though the distance between two interfaces is much smaller. The last one, case 4. This is the case that unstable density stratification exists, and Moore's condition is satisfied. And this is the interfacial shape, and this is the velocity field. Even if Moore's condition is satisfied, the effect of gravitational instability is stronger, and lower sheet begins to roll up at the early stage and affected by the upper sheet, even though the Moore condition is satisfied. This is the movie of that Moore's condition is satisfied, case 1 and case 3. And at least KHI of one interface is suppressed when the two interface flow satisfies Moore's condition. This is summary. When Moore's condition is satisfied, the velocity field between the two interfaces becomes the standard flow. Therefore, the two interfaces are hardly affected by each other's vortex-induced velocity, and they tend to evolve independently, even in the nonlinear regime. When Moore's condition is not satisfied, both interfaces roll up at quite an early stage. But when the gravitational instability is considered, RTI occurs, and two interfaces strongly interact with each other, even if Moore's condition is satisfied. That's all. Thank you for your attention.
And the session is now open for questions. Yes.
So the potential application of your model is Richtmyer-Meshkov instability, right? Or an interplay of Rayleigh-Taylor and Richtmyer-Meshkov instability in a complex medium, right?
I didn't explain Richtmyer-Meshkov instability because I have no time. So that's an interesting question, good question. Unfortunately, the Richtmyer-Meshkov instability cannot stabilize with this method, unfortunately, because in the Richtmyer-Meshkov instability, initially there is non-uniform velocity shear exists. Anyway, Moore's analysis or Moore's conjecture is realized when uniform velocity shear exists initially, but Richtmyer-Meshkov does not satisfy that condition. So unfortunately, Richtmyer-Meshkov instability does not stabilize with this method.
There are more questions. Yes.
Not a question, more a remark. It is possible to produce very uniform shear with Richtmyer-Meshkov instability. That's what my talk was about. Unfortunately, the configuration that I presented in that talk would not satisfy Moore's condition, but that would not be because of shear non-uniformity, but because of the direction of rotation of vortices.
Is that a question or? Thank you for your comment.
Are there more comments or questions?
Thank you for your kind comment.
Okay, thank you very much. A very interesting talk.
Thank you.